So chapter 3 has 3 important themes that I'd like for you guys to go over. One of them is the mole. Okay, so that's very important. Okay, number 2, we're going to balance equations. And number 3, we have limiting reactants. Okay, so this is something that we want to talk about here. So we'll go over these 3 main topics. And before we do that, let's talk a little bit about this idea of average atomic mass. Okay, that's this bottom number. Okay, so this bottom number has 3 meanings. Okay, anybody know what's one meaning? Okay, 1 mole of carbon contains how many grams of carbon? And what are the units? Grams. Okay. So 1 mole carbon, 12.01 grams of carbon. Okay, same thing, 12.01 grams of carbon, 1 mole of 12.01 grams of carbon, 1 mole of carbon, same thing. All right, the second meaning for the exam that's coming up, it's a mass number. So it's the number of protons and number of neutrons. Okay, mass number. And then finally, this is also a weighted average. Okay, weighted atomic mass. I'm going to put here weighted average. It's a weighted average. Okay, so this means it's not 12, but 12.01. What does that mean? Okay, it means that we have a version of carbon that's 12, and then we have a version of carbon that's about 13 carbon. Okay, so which do you think you have more of the carbon? Carbon 12 or carbon 13? All right. Okay, 12.01. It turns out that this is 12 AMUs, or atomic mass units, and it's about 99% of the carbon in our planet. A little bit is 13 AMUs, and this is about 1% natural abundance. Okay, so the thing is, this carbon-13, that's only 1% natural abundance, also contributes to that mass. That's what we mean by weighted average. Okay, that 13 AMUs, that carbon, that's 13 atomic mass units, it's 1% found in our planet, and that also goes into that number. Okay, that also goes into this number, and that's why it's 12.01, not just plain old 12. Okay. What are carbon 12 and carbon 13 called? Okay, for the exam Thursday? I think I heard it. What are they called? Okay, what is the meaning of isotopes? Same element, different number of neutrons. Okay, how many neutrons are in carbon 13? Neutrons. 7 is the right answer. Very good. And how many neutrons are in carbon 12? 6 neutrons. Okay? Very good. All right, let's do a problem involving isotopes here. Let's do a problem involving isotopes. I'm going to go on to the next page. Okay, we'll do a problem involving copper. And in this particular problem, the idea is we're looking at weighted average. How do you calculate a weighted average? This is what this number is. It's a weighted average. Okay, you don't just do an average and say, oh, I'm good, I'm done. This is weighted. There's a difference between weighted average and the average that you learned in math. So the atomic mass of two stable isotopes of carbon. We have a 6329 carbon. Okay, which is 69.1% natural abundance. Okay. And then there's a 6529 copper, which is 30.83% natural abundance. Everyone see that? I'm just writing this out here. We're doing a weighted average problem. Okay, the atomic mass of the 6329 copper is 62.9296 AMUs. Okay. So this weighs 62.9296 AMUs. This AMU stands for atomic mass units. And how much? And the 6529 isotope of copper weighs 64.9278 AMUs. Okay, so what is the average atomic mass of copper? Okay, so we're not going to average them. Okay, are we going to average this, Emily, and divide by 2? Add and divide by 2? Okay, no, because it's weighted. Okay, so we have to incorporate the weights. We have to incorporate the natural abundances. All right, so this is how we'll do this problem. Okay, we'll first do the 62.9296 AMUs. And this is 69% natural abundance. So I'm going to make that into a decimal. Okay, the way I do that is I'll move it to 2 places to the left. So 69.17 is the same thing as 0.6917. Plus, so this is the contribution of, this guy is the contribution of 6329 copper. And then we have the contribution of 6529 copper, the other isotope, and that is 64.9278. And this is 30.83% present in nature. So I'll just convert that to a decimal. Okay, converting it to a decimal is easy, just divide by 100. So this makes it 0.3083. Okay, this is from 6529. Okay, so the contribution of this isotope and its weight, the contribution of that isotope and its weight, we will add them together, and this should give us the answer. Okay, so 62.9296 times 0.6917, 43.528, something like that. Okay, plus this one, 64.9278 times 0.3083, 20.017, just adding some extra digits here. And let's add those two together. $63.545 AMUs. This is our answer. Okay, and it's pretty close to what I get from the periodic table. Okay, it's pretty close. Okay, copper is 63.546. And then we calculated it from this problem as 63.545. Okay. So this is how you calculate a weighted average. Okay, and I think you'll do this for your lab this afternoon. Okay, in which again, like I want to say, for those that came in late, you can do it at home watching the video. Any questions? Okay, so that's one important facet of this number, okay, is that it's a weighted average of the isotopes and their abundance. Once again, it's the weighted average of the isotopes and their abundance. So let's move on to page 3. All right, let's now talk about the mole. Okay, very important thing here in this class in chemistry. Okay, you may have heard of length being a meter, mass being a kilogram, time in seconds, minutes, hours. Never heard of this, okay? Mole. Okay, this mole means an amount of a substance. It's an amount. Is it the same as weight? Yes or no? No. Okay, mole is the amount. Weight is something else. In fact, 1 mole is 12 grams of copper. 1 mole is 12 grams of copper. Okay, so it's the amount. It's not its weight. Okay, so it's a totally different unit. So we need to understand what a mole equals to. Okay, we need to understand what a mole equals to. So there's 4 things, 4 relationships. Okay, 4 relationships. So what do I mean by relationships? Okay, I mean conversion factors. You know, 4 quarters is $1. Isn't that $1, 4 quarters? Anything else you can think of? 12 eggs is a dozen. 100 pennies is $1, right? Okay, so like this, we want to do the same things for a mole, okay, so that we can convert, right? So there's 4 things that I want you to know. Let's first go over definition 1. 4 relationships. Okay, the first one is something that we already went over, okay? The molecular weight of the substance in grams per mole. Okay, so 1 mole of O is about 16 grams, right? How about 1 mole of glucose? Okay, C6H12O6 is glucose. Okay, how did they get 180 or so? How did they get that number? Okay, what's carbon? Okay, what do they multiply it by? 6 plus, what's hydrogen? Times what? 12. What is oxygen? 15.99 or 16.01 multiplied by what? Add them up and what will you get? About 180.04, 180.01, something. Okay, you're looking around 180. So are we comfortable doing this? Shall I give you one more? Okay, 1 mole of KCl. How many grams are in 1 mole of KCl? Okay, so get your periodic tables out. What is potassium? K? 39.909. I'll just go 39.10. That's fine. grams per mole. What is Cl? 35.45. Okay, so add, what's 39.10 plus 35.45? 74.55, something like that. Okay. So if I give you 74.55 grams of potassium chloride, how much did I give you? 1 mole. This is correct. 1 mole. If I gave you 1 mole of KCl, how much did I give you, Emily? In grams, I gave you 74.55 grams. Okay, this is 4 quarters to $1. 1 dozen, 12 roses. 100 pennies, $1. Okay. Okay. So if you get this relationship right, then the answer will be right. Okay, on their homework problems. Okay, so is everyone confident on this first definition? Okay. Is it okay? Shall we move on to the second one? Okay. Just add up these numbers. Add them up. Okay, add up these numbers. If there's a 2, multiply it by 2. If there's a 6, you multiply it by 6. Okay? All right, definition 2. Okay, this is a little tricky. 1 mole is equal to Avogadro's number of particles. Okay, Avogadro's number. First of all, what is Avogadro's number? Okay, it is going to be 6.022 times 10 to the 23. Maybe I will give that to you on the exam, but it won't hurt to memorize it. It won't hurt. Atoms, but it can also be 6.022 times 10 to the 23 molecules if we're talking about molecules. It can also be 6.022 times 10 to the 23 ions if we're talking about ions. So let's talk about ions first. Okay. So on the exam, elements in group 1A for Thursday's exam, what charge will they like to be? Okay, so if sodium were to form an ion, Gerardo, what charge would it be? Okay, correct. So now my question to you is 1 mole of sodium ions contains how many ions of sodium? 1 mole of sodium ions contains 6.022 times 10 to the 23 ions of sodium. All right. 1 mole of KCl. KCl is a molecule. Okay. How many molecules are in 1 mole of KCl? Molecules, not grams. Molecules. Not grams as above, but molecules. 6.022 times 10 to the 23 molecules are in 1 mole of KCl. So if I give you 74.55 grams of KCl, I gave you 1 mole. How many molecules of KCl are in there? 6.022 times 10 to the 23 molecules. Okay. I'll put it, it doesn't matter if I put it in the, it does not matter if I put it in the numerator or denominator. But 1 mole, let's look at Fe. This is iron. Okay, how many iron atoms are in 1 mole of iron? How many iron atoms? 6.022 times 10 to the 23 atoms of iron are in 1 mole of Fe. Okay, atoms, molecules, or ions. If you're dealing with an ion, 1 mole of that ion contains that many ions, Avogadro's number. A compound or a molecule, 1 mole of water, 1 mole of KCl, 1 mole of glucose, 1 mole of sodium chloride contains how many molecules of water, glucose, sodium chloride? This many molecules. 1 mole of iron, 1 mole of cobalt, 1 mole of any element contains how many atoms? 6.022 times 10 to the 23. Yes, go ahead, sir.
It's different if it's, for example, an alkaline earth metal that has 2 ions.
It would still be 6.022 times 10 to the 23rd. Like here, 1 mole of calcium contains that many ions of calcium. Now, where it would be different would be 1 mole of O2. Okay, 1 mole of O has 6.022 times 10 to the 23 O atoms. But because oxygen natural abundance is O2, we actually have to multiply this by 2. Okay, we have to multiply it by 2. So this becomes that 1.20 times 10 to the 24. Okay, this would be oxygen is a molecule. Okay, molecule. So this is the second definition. It's Avogadro's number. Okay, I'll give that number, but it's good if you know it, but if you don't want to know it, I'll give that. It's 6.022 times 10 to the 23. Okay. So are we okay with these conversions? When will we use Avogadro's number? When? And in what case or what scenario? When will we have to use this number? Yeah, to find the number of to find the number of molecules, ions, or atoms in the substance. Very good. Good job. Right, that's when you're going to use this Avogadro's number of 6.022 times 10 to the 23rd. All right, any questions on definition 2? What's definition 1? Add up those numbers in the periodic table. What's definition 2? Avogadro's number. Let's look at definition 3 now. Okay, definition 3 is part over whole. Okay, part over whole. Okay, or whole over part. Okay, I want you to teach you that you can use these. You can flip it because that's what a conversion does. You can use it this way. $1 is 4 quarters, or 4 quarters is $1. So we'll take an example of water here. Okay, for every 1 mole of water, how many moles of hydrogen are there? For every 1 mole of water, how many moles of hydrogen? It's 2. 2, very good. Okay, this is the whole, that's the part. For every 1 mole of water, how many moles of oxygen are there? 1. is the right answer. Okay. So that is the part over whole situation. How about, let's give another example here. 1 mole of Fe2O3. 1 mole of this whole rock that we call Fe2O3, iron 3 oxide. Okay, how many moles of iron is contained in that? 2. Okay. So that is our third definition. When will we use this? Okay, we will use this when we want to find out how many moles of the atom are in the whole thing. Okay? So if we want the moles of the part out of the whole, like I said, part over whole. Okay, so these are the conversions that we should familiarize ourselves with. Part over whole. Part over whole. By the way, there's a mistake here. 1 mole of C3H8O should have 8 moles of hydrogen. Okay, so sorry about that. So what's the first definition of the mole? Quick, answer fast. Add the weights. Okay, very good. Okay, grams over mole. 1 mole is that many grams. What's the second definition? Okay, and what are the units? What are we trying to calculate? Molecules, atoms, ions. Okay, and what's this third definition? Yes, the part, how many moles, part over the whole amount. Yes, part over the whole amount. Okay, so that's the third definition. Okay. All right, the final definition is the coefficients of a balanced chemical equation. So let's balance some equations, shall we? That's the enthusiasm I love to hear. Balancing equations, okay? There's this dropped silence. All right, let's balance some equations. I'm going to balance this equation here. Okay, so let me rewrite it. I'm going to rewrite it here. Okay, we'll balance this together. Okay, we'll take C6H12O6. This is called glucose. Okay, not something you need to know in this class. We will react it with oxygen. It will combust. And this will be CO2 plus water. So first thing I want to tell you guys is that the way we write equations in chemistry is that reactants go to products. Okay, so here to the left of the arrow are called what? Reactants. Okay, then you draw this arrow and they go to products. So this is our first chemical equation. First thing is that reactants go to products. Okay, the second thing is that we need to balance this. Okay, we need to balance it. What do we mean by balancing it? First off, this is super important. So if you don't listen to anything I say, listen to this. Actually, listen to everything I say. But this one you should. Okay, you don't change these numbers. You don't change the 2, you don't change the 2, the subscripts, you don't change the 6 in the carbon. The only thing you can do is add a number to the front of the whole thing. Okay, because when I grade it, and I've been here at Methodist for 9 years almost. Okay, so I've seen things. They'll change this number, the number. Okay, you leave the formula intact. Okay, don't mess with it. The only thing you can mess with is the number out in front. The only thing you can mess with is adding a number out in front. Okay? And now, how do we balance it? Okay, let's just balance it. Okay, we want the number of atoms in the reactants to equal the number of atoms in the products. Because remember, all the way back in chapter 1, we said that you cannot create matter, cannot destroy matter. I think we said that. You cannot create energy, you cannot destroy energy. Okay? Everything has to be accounted for. Everything has to be accounted for. In this case, we're going to account for every atom. All right? So the only thing you want to mess around with is the numbers out in front. Okay? Equal number of atoms in the reactants, equal number of atoms in the products. All right, so let's just draw an imaginary line. So the elements that we have in the reactants are carbon, hydrogen, and oxygen. The elements that we have on the product side, well, they better be the same thing because we cannot create or destroy atoms. Okay, so how many atoms of carbons do we see here? Good. How many hydrogens? 12. How many of oxygens? 6 plus 2 is 8. Okay. All right. How many atoms of carbon here in the product side? 1. Very good. Hydrogen? 2. Oxygen? 2 plus 1 is 3. Okay. So I wish I can tell you guys, follow this, follow that, and you'll balance it. But I can't. Okay, this is just pure, puzzles. Okay, trying to solve the puzzle. Some of them are easy, and some of them are hard. So I recommend, like I used to tutor a long time ago, I recommend just going trial by error. Okay. One thing I've learned is you always want to balance this one last, the loner. Why would you want to balance the loner last? Because if I put a number here, I'm only affecting oxygen. If I put a number here, I'm affecting the whole thing, carbon, hydrogen, oxygen. So probably balance this last if I were to, give some advice. To me, I go with the easiest thing because there's no, I can't teach this other than try. So to me, the obvious one is to go for the carbons, 6. Okay. Remember, we only put numbers in front of the molecule, correct? All right, so how many carbons now? How many hydrogens? 2. How many oxygens? 13. Okay, 13. All right. Now, to me, I'm going to go for the hydrogens if I put a 6 here. If I put a 6 here. And if I put a 6 here, how many hydrogens do I have? 6 times 2 is 12. Okay, very good. Now, how many oxygens do I have? You're Samantha, right? How many oxygens do I have? What's 12 plus 6? Okay, so what can I put in here to get to 18 oxygens? If I put a 6 here, 6 times 2 is 12, 12 plus 6 is 18. You're right. Okay, we balanced it. So 6 carbons, 12 hydrogens, 6 times 2 is 12. And what's 6 plus 12? 18. What's 12 plus 6? 18. So this is balanced. Okay, so we balanced our equations. Okay, good job. Now let's go back to the fourth definition of the mole. Okay, the coefficient of a balanced chemical equation. So this is the coefficient. What's the coefficient here? 1. What's the coefficient here? Coefficient here? Coefficient here? 6. Okay, so for how many moles of glucose give you how many moles of CO2? Do you know this, David? For every 1 mole of glucose C6H12O6, how many moles of CO2 will I get? 6. For every, how many moles of oxygen do I get moles of water? For every 6 moles of oxygen there is of water, which actually reduces to 1 to 1, which this reduces. Anything else you can think of? How many moles of C6H12O6 react with how many moles of oxygen? For every 1 mole of C6H12O6, how many oxygens react? 6 moles of oxygen is the answer. What is the mole ratio of the products? For every 6 moles of CO2 there is 6 moles of water. Okay, do we get this? For every 1 mole of glucose there is 6 moles of water. For every 6 moles of water there is, you get the point. Okay, so that is the last definition. Okay, so this is something we want to highlight for ourselves. So these are the relationships. Okay, if you get the problem wrong, when I notice, because you get the relationship wrong. It's not 5 quarters is $1, right? It's 4 quarters is $1. Okay, it's 1 mole of glucose to 6 moles of CO2 because we balanced it. Okay, so we want to get our relationships right, and we never mess around with this number. Okay, we never mess with the actual formula. Okay, we just mess with the number out in front. Okay, this number out in front, the coefficient, can also be a fraction. Okay, this coefficient can also be a fraction. We'll go over some of those later today or next class. It's possible it can be a fraction. Okay, what time do we have? Timekeeper. What time do we get off? 10:45. Oh, okay. All right, let's do some problems together here. All right. All right. Are there any questions? Okay, yes, sir.
Does it have to be like simplified, like the lowest, like?
Yes, you can. If you can, you can. Are you talking about these numbers? Yeah, if you can reduce it, you can reduce it. Yeah, it's a very good point. Yeah. If you can reduce them, you can. Yeah. All right, calculate the number of grams of lead in 12.4 moles of lead. Okay, grams of lead to moles of lead. Okay, guys willing to do this here? Can we do this? How will we do this? Yes, we will add the atomic weights. Here we're only looking at lead. Okay, so start with what we are given, 12.4 moles of lead. Okay, 1 mole of lead contains how many grams of lead? Okay, for this one, we will look for lead in our periodic table. And it's 207.2. Everyone see that? $207.2. Okay. So I like canceling out units. So the moles of lead cancels with the moles of lead. And what's 12.4 times 207.2? 2569, 3 sig figs maybe. So you can go like this, grams of lead. You can even go 2.57 if you want 3 sig figs times 10 to the third grams. Okay, I'll take either one. That's fine. Sorry. But make sure you put your units, right? So we cancel out the moles and we got grams. All right, let's do the next one here. What is the mass in grams of 31 atoms of gold? 31. Okay, 31 atoms of gold. All right, so start with what we are given, which is 31 atoms of gold. Okay, 1 mole of Au contains how many atoms of Au? 6.022. Very good. Okay, everyone see that? Okay. 1 mole of Au is 6.022 times 10 to the 23rd atoms of Au. Okay, what's our next conversion? We want it to grams. So 1 mole of Au contains how many grams of Au? Uh, 196.97, something like that. And then things cancel out. The atoms cancel out with the atoms. The moles cancel out with the moles. Okay, so what's 31 times 196.97? Divided by Avogadro's number. So divided, I put parentheses, 6.022 times 10 to the 23rd. Close those parentheses. 1.01 times 10 to the minus 20 grams. And this is our answer. Are we comfortable doing this? Okay, when you see atoms, what should automatically come to your head? Okay, Avogadro's number. Okay, Avogadro's number. All right, calculate the number of moles of chloroform in 198 grams of chloroform. So 198 grams of chloroform. Okay, 1 mole of chloroform contains how many grams of chloroform? Okay, so carbon is about 12.01, hydrogen is about 1.01, chlorine, let me check that really quickly, 35.45. Okay, what do we need to do with that 35.45 of chlorine? Times 3. Okay, so 12.01 plus 1.01 plus 34.45 times 3. About 116.37. All right, the grams of chloroform cancels out with grams of chloroform. And what do you guys get? 198 divided by 116.37. About 1.70. Okay, 1.70 moles. Yeah, 1.70 moles of chloroform. So if I give you guys 1.70 moles of chloroform, how many grams of chloroform did I give you? 198. If I gave you 198 grams of chloroform, okay, how many moles of chloroform did I give you? 1.70. Okay. All right, let's do 2 more problems here, and then we'll move on to something else. Are we doing okay? Or is our stamina being tested? Let's see if we can get to a couple of more pages here. Okay. I have the time here. 10 o'clock. All right, determine the molecular mass and molar mass of citric acid. How many hydrogen atoms of citric acid are there in 10.01 grams of citric acid? Okay, so this is a complicated one. First of all, the molar mass is grams per mole. Okay, and then the molecular mass, it's AMU. It's the same number, just different units. Okay, same number, different units. So we have citric acid here, and we have 10.01 grams of citric acid, and it's asking for, in that 10.01 grams, how many hydrogen atoms? That's crazy. Okay, I gave you 10 grams of this powder, and it's asking you how many hydrogen atoms are in that powder. Okay, citric acid is like a powder. So let's solve this here. So we have 10.01 grams of citric acid, which is H3C6H5O7. Let's go ahead and convert that to moles. 1 mole of H3C6H5O7. It contains how many grams? Okay, that's this big one here. What's hydrogen? Times 3. We got a carbon, which is 12.01 times 6. Okay, we got another 5 hydrogens. Hydrogen is about 1.01 times 5. And then we got O7. And oxygen is about 16.01. Don't forget to multiply that by 7. 112.07. Let's add these up here. 3.03 plus 72.06 plus 5.05 plus 112.07, about 192.21. Okay, so 1 mole of citric acid is 192.21 grams of citric acid. Okay. Okay, now it's asking for hydrogen atoms. So 1 mole of this okay, 1 mole of citric acid contains how many moles of hydrogen? 8. 1 mole of citric acid contains 8 moles of hydrogen. This is part-whole relationship. And now we can use the fact that 1 mole of hydrogen contains how many atoms of hydrogen? Okay, so the grams cancel. The moles cancel. Moles of H cancels out with moles of H. And what are we left with? We are left with atoms of hydrogen. See how everything nicely cancels out? So 10.01 times 8 times 6.022 times 10 to the minus 10 to the 23rd. Okay. Is equal to that number, and we're going to divide it by this. .51 times 10 to the 23rd is what I am getting. So there's 2.5 times 10 to the 23rd hydrogen atoms in 10.01 grams of citric acid. Okay. Right, are we getting this math? Is it okay? All right. Let's finish up a couple of more pages here before we meet up again. Calculate the number of grams of aluminum in 371 grams of Al2O3. What's the formula of this? Aluminum what? This is called aluminum oxide. That's correct. Okay, very good. So grams of Al and 371 grams of Al2O3. So we'll start out with 371 grams of Al2O3. Okay, let's convert that to moles. So 1 mole of Al2O3 contains how many grams? We should know this by now. What is Al? .982, something like that. What is oxygen? 16.01 times 3. Oh, what do we need to do with the Al? Times 2. Okay. Right, 26.98 times 2. 16.01 times 3, 48.03. Okay, so what happens when we add them up? 101.99, 102 almost. Yeah. Okay, so we got grams to moles of Al2O3. How will we get to grams of Al by itself? Grams of Al alone? Huh? Yes, part overhaul. Very good. Thank you. So for every 1 mole of Al2O3, there's how many moles of aluminum? 2 moles of aluminum. And to get to grams, 1 mole of Al is how many grams? I think we already 26.982 grams. Right, let's cancel out our units. Grams of Al2O3, grams of Al2O3, moles, moles, moles of Al cancels out with moles of Als. What do you get here? Okay, we have 371 times 2 times 26.982. Okay, divided by 101.99. 196 grams. Okay, so this 196 grams of Al are in 371 grams of Al2O3. All right. So this is stuff that will carry you through Chem 2 for those of you that are taking Chem 2, but I think there's only one taking Chem 2. So, yeah. All right, so, yeah. Any questions or comments here? Let me check the time here. I got another 10 minutes. Let me just lecture for 10 more, maybe 5 to 10 more minutes. I'll try to get 2 pages done, and then we'll go. Okay, I'm going to move on. All right, let's just do pages 7 and 8, and then I will let you guys go. All right, percent composition. All right, so if you take C2H6O, okay, this is called ethanol. How much percent carbon is in ethanol? You see what they did? They took 2 times 12.01 and they divided it by 46.07, part over whole. Where do you think the 46.07 denominator comes from? It's the atomic weight, okay? And we get a percentage by multiplying it by 100. So percent oxygen, there's 6% hydrogen, excuse me. We have 6 hydrogens, each one is 1.008 grams. That divided by the total, multiply it by 100, we get the percentage hydrogen. 1 oxygen in ethanol. Okay, let me just write that this is ethanol. Okay, 1 oxygen. The oxygen weighs 16 grams divided by the whole thing, which is 46.07, the atomic weight, multiplied by 100. This is the percent oxygen. So you add all these up, you'll get 100%. Okay, so percent composition. All right. They must all add up to 100%. Take the molar mass of the element and divide it by the molar mass of the compound. All right, we have molecular formula and empirical formula. And this is just very simple. The empirical formula is the lowest common denominator, okay? Reduced. Think of the formula as being the most reduced. Okay, the molecular formula is the formula as it is. Okay, the formula as it is found in nature. Okay. As it is. So as an example, let's look at C6H12O6 glucose again. Is there a way we can reduce this?
Yeah.
How can we reduce this?
Divided by 6.
Okay, so we reduce this by dividing by 6. So the empirical formula is CH2O. We're dividing it by 6. So we can get back the empirical formula, we can get back to the molecular formula just by multiplying it out. So you do like you do in math. Okay, so that's one molecular formula. We can multiply the empirical by 3. We get another formula. We can multiply it by 4. We can multiply it by 5. Yes, we can even multiply it by 6. Okay, and get back our glucose, or whatever the name of that compound is. It is glucose. So empirical is the lowest common denominator. One thing I want you guys to know, the molecular formula and the empirical formula can be the same. Take, for instance, water. What's the empirical formula for water? You cannot reduce it anymore, so it's going to be H2O. Okay, you cannot reduce H2O anymore. So here, the molecular formula, which is water H2O, is the same as the empirical formula because you cannot reduce it. If you can reduce it, reduce it. If you can't, no problem. Okay? No issue. All right, let's do one problem and then we will go. Okay? I'll let you guys go. Okay, we did 8 pages today, so. Okay, well, this will be our final page for today. All right, here's our problem. Okay, sample of compound contains boron and hydrogen, and it contains 6.44 grams of boron and 1.803 grams of hydrogen. Okay, boron, this is called boron, it's 6.44 grams, hydrogen 1.8 or so grams. The molar mass of the compound is about 30 grams per mole. It actually should be grams per mole, molar mass. What is the molecular formula? Okay, what is the molecular formula? So we have an unknown. This is actually done in the field. Imagine you get some drug from the soil, or you isolate a drug. You want to know its formula. So this is one way you can do that. This thing has boron and hydrogen. So it's some formula that has boron and hydrogen. Right, we know we have 6.44 grams of boron, so let's go ahead and convert that to moles. Okay, 1 mole of boron contains how many grams? Boron. 10.811 grams. Contains boron and hydrogen. Okay. Do you see the 10.11? Do you see the 10.11 boron? Okay. Grams cancel. So what do we do when we get that? .596 moles. let's do the same for hydrogen now. Hydrogen is 1.803 grams of hydrogen. 1 mole of hydrogen. What is hydrogen? It's about 1.01, right? Okay, we'll go with 1.01. Yeah, we'll go 1.01 grams. .785 moles of hydrogen. All right, so our formula is this the right answer? Boron 0.596, hydrogen 1.785. Is this our answer that we will put on our exam or our quiz or our homework? What's one of the first rules of our chemical formulas? No decimals. Very good. Okay, so we need to get those decimals out. Okay, and so the way we do this is we do a math trick. Okay, are there any math majors here? Okay, the way we do this is we do something called normalization. Have you heard of normalization? Okay, normalization is when you force the lowest one to the number 1. When you force the lowest number to 1. Okay. Okay, this is called normalization. Basically, you divide by the lowest number. Okay. Okay, when you divide by the lowest number, you force that lowest number to 1. So this becomes boron B. What's 1.785 divided by 0.596? 2.99. I think it's safe to call it 3. Okay, we'll just call it 3. 2.99 is 3. Okay. But is this the right answer? Okay, notice the molecular weight. This is not the molecular formula. It is the empirical formula. Okay, the way we get the actual molecular formula is that we need to know the weight. Okay, the weight of this is 30 grams per mole. Okay, 30 grams per mole. So what's the weight of this? Okay, boron is 10.81. Hydrogen is 1.01 times 3. Okay, so the molecular weight of BH3 is about 13.84 grams. Okay. Okay. What is the actual molecular weight of the unknown compound? So our empirical formula does not match the weight of the molecular formula. So I'm going to multiply it by the number 2. I'm going to multiply it by 3. I'm going to multiply it by 4. I'll try 2 first. Okay, this is our empirical formula. And I'm going to get B2H6. What's the molecular weight of B2H6? Okay, so we'll take the 10.811 times 2 plus H6. Hydrogen is about 1.01 times 6. Bless you. 27.68 I think that's good enough, close enough match to 30. So the molecular weight of this is 27.68 grams of B2H6 per mole of B2H6. And I think the correct answer for this formula is B2H6. Okay, it's closing. It's about molecular weight of 28, 27, and this is 30. So yeah. Okay, so this is our answer.